And this is where, unfortunately, the terminology that we use is archaic, it's old, and it sucks. But it's so entrenched that we're going to use it. Voltage. First of all, some review. So here's a charge, here's a field point. A says, find the electric field and direction. 75 centimeters east of a 2 microcoulomb charge. So we have two ways to find electric field. Electric field is the force per coulomb, and it's from your formula sheet, KQ over R squared. Which one am I going to use? And part of what you're going to need to figure out is how to know what to use when. So some hints. What's that right there? Distance, a displacement, or a radius? So I'm kind of leaning towards, this is the one that we use if we know the charge that's creating the electric field, the big planetary charge. This is what we use to find the electric field if we know a force at that location on a given charge. So, to find the electric field, it's going to be KQ over R squared. It's going to be 9 times 10 to the 9th, 2 microcoulombs, all over 0.75 squared. And I get an electric field of, anyone else? Is 32,000 correct? Double check me, please. Mixed nodding, okay. 32,000 what units, please? It pops out of this version, newtons per coulomb. Direction. Which way would a positive right there want to move if it could? I heard someone say right, I heard someone say left. I'm pretty sure one of them's wrong. This charge here, positive or negative? So what would a positive there do? Repel or attract? So it's going to move to the right or east. What else could I ask you? I could say, you know what? Let's skip B. Let's do C. Find the force on a 2 coulomb, that's a huge charge, on a 2 coulomb charge placed at that point. Now, I could, put your pencils down, look up, could go like this. And then I could go, don't write this down. And if they had given me part C with no preamble, with nothing before, I'd do it that way. But what did I find in part A? What did I find in part A? Electric field. Hey, I have an equation that relates force and electric field. Get the F by itself, please. Get the F by itself, please. Another way to find electric force is if I know the charge at that location, which apparently is 2 coulombs, a huge charge, and I know the electric field at that location. Shaq, what was the electric field at that location? That's our answer from part A. You know what? I can do this in my head. Shaq, what is 2 times 32,000? Well, what's 2 times 32? Add the 1,000, 64,000 newtons. Direction, it would feel a force attracting it. Okay? I'm just going to do A and C. That's kind of jogging our memory, what we've done so far. So, Mac, the electric field tells us how many newtons of force per coulomb at that location. Turns out, Rafi, for energy, there's a similar or analogous concept. It tells us how many joules of energy per coulomb. Joules per coulomb. Not newtons per coulomb, joules per coulomb. This is commonly called potential, not potential energy, potential. But it's also called voltage. And it's given the symbol V for voltage. Here's the problem. Potential and potential energy are not the same thing, and kids are going to get them mixed up. So the units of potential or voltage are joules per coulomb, which is the definition of a volt. We must be very careful not to confuse potential, joules per coulomb, with potential energy in joules. So this is the definition. This is the definition of a volt. A volt, 1 volt, is defined as the amount of potential energy per coulomb. In fact, 1 volt is 1 joule per coulomb. That's 1 volt. There's our definition. The higher your voltage at a location, Mac, what you're saying is every charge has more energy at that location if it's at a higher voltage. If you're at that same location but it's a lower voltage, you don't have as much potential energy per charge. The difference between a 3-volt battery and a 6-volt battery is not how much charge, it's you're saying each charge has more energy, can do more work. Example 2 says, fill in the, so this is the definition of a volt, energy per coulomb. It says, fill in the proof to find the potential or voltage due to a point charge Q. Well, potential energy is K big Q little q over R. And since voltage is how much energy per coulomb at that location, it's really K big Q little q over R over Q. Hey! So in the first box, Jordan, was the definition of what a volt is. It's how much energy per coulomb. In this next box, we can now write how to calculate it. It's going to be KQ over R. You want to know the voltage at any location? So when I was doing my little electric field toy, I was also, it turns out, sending out or creating a voltage. The voltage at any location would have been the charge on that electric field toy times 9.9 times 10 to the 9 times K, divided by how far away I was. The further away, the less voltage at that location, the less energy per coulomb each charge has. Big deal. Actually, hugely useful. By the way, scalar, which means we're going to put signs in. If we have a negative charge, Rafi will have a negative voltage. If we have a positive charge, we'll have a positive voltage. Let's try some. So I'm giving you almost the same picture as example 1, but now let's see what we can do in terms of scalar stuff. Nate, what does A want me to find? Find the potential. Did it say potential energy? This is my big P. This is the one, I don't know if you remember, before the break I said time and time again on the test, I'll ask for one thing and kids will give me another. What it is I'm going to ask you to find the potential. And if you tell me the potential energy, unfortunately, I have to give you 0 out of 7. Because that's like me saying, find the acceleration, and you saying, I found the distance. And that's great, and you may have done it right, but it's nothing to do with what I asked for. So you have to read very carefully. Now, got another problem. We've already been using the letter V for something else since Physics 11. What's V stood for? Velocity. So my physics prof, to distinguish the two, for a capital V, he always put little wings on it like that, because that's the symbol for voltage. And the reason I'm doing that is in a few minutes, we're going to have an equation that has V and V in it. So, good habit to get into. Voltage is KQ over R. It's 9 times 10 to the 9th. The charge creating the voltage is 2 microcoulombs. Positive or negative? Positive. If it was negative, I'd put a negative in. All over 0.75. How many volts are there at that location where the dot is? By the way, generally you're going to find volts are in the hundreds or in the thousands, sometimes in the tens, but usually in the hundreds or the thousands. Right there, it's 24,000 volts. 24,000 volts. Direction, it's a scalar. It's a scalar. Again, we're going to skip B. We're going to go straight to part C. Nate, I'm going to pick on you again. What does part C want me to find? This is why I use capital P, capital E for potential energy, to make it look different from potential, even though that's wrong technically, but anyways, okay? What does it want me to find? Put your pencils down. I could do this. Don't write this down. And that would be perfectly acceptable, Rachel. And if I hadn't done part A, that's what I would do. But what did I find in part A? Nice and loud. Say it again, kiddo. Is there an equation that has potential energy and voltage in it? Could you rewrite that equation to get the PE by itself, please? How? Okay. Up here, if you want to, you can make a little note. PE also equals QV, and I'll put the wings on there to emphasize that it's not a velocity or a speed, it's a voltage, because this is the one that's going to often show up in the same equation as a speed. That one's not on your formula sheet, I don't think, is it? QV equals PE? No, but V equals PE over Q, that one is on there, is it not? Yeah. Okay, so it's sorted there. And why would I use that? Well, because I have the voltage at that location. Pick your pencils up. You know what? The potential energy is just going to be the charge at that location times the voltage at that location. I'll take that. The charge is 2 coulombs, a huge charge. The voltage is 24,000 volts. You know what, Shaq? I'll bet you can even do this one in your head too. 48,000 what? Now ask, what did we find and what units go with that? What did we find? Potential energy. So this is joules. Well, oh yeah, I guess if volts is how many joules per coulomb, if you have 24,000 volts, which is 24,000 joules per coulomb, 2 coulombs will give you 48,000 joules. Okay, that makes sense. What? Oh, question C, thank you. I'll skip D, but it'd be the same idea. So, here's what else that means. If we know the change in voltage, or potential difference, what does the word difference mean in math? First of all, what's change in? What's change in anything? Final minus. Difference is a word for minus, so that's another way to say change in voltage. And this is some of the archaic terminology that has still stayed with us for 150 years from the first discoverers of electricity. So if you do take an electronics course, they'll talk about potential and potential difference all the time. Even though I'm not a big fan of that terminology, Naomi, I understand why they do. And when you really wrap your brain around it, it does become clearer. I just kind of, anyways. We can find the work. Why? Well, right? And if VI equals VF equals 0, those are lowercase v's. How can you tell they're lowercase v's? Because if they were uppercase v's, what would I have put on them? Little wings. If your initial and final speed are 0, what's that mean in this equation? Okay. Right? Now that's not new. But I just gave you a different way to write potential energy, Rachel's formula. Rachel, you said it was right? Or sometimes you'll just see it written as this, Q change in voltage, because it's V final minus V initial if you factor out the Q. It's another way now. And that can be a nice way to calculate work if you happen to know the voltages at two locations. It's certainly way faster than going KQ1, Q2 over R, KQ1, Q2 over R. It is. Example 4. No. Scalars, so who cares about the angles or the directions or the fact that it's diamond-shaped? I wouldn't care if it was star-shaped or X-shaped. I just care about before and after because it's a scalar. Now, if this was an electric field or a force, ugh. Mac, what does A want me to find? Potential energy or potential? Just potential. So potential, which is voltage, that's going to be KQ over well, okay. Look up for a second. Really what I should do, Grayson, is I should find the voltage or the potential from that guy. And I should find the voltage or the potential from that guy. But Grayson, what do you notice about both of the charges? They are. What do you notice about both of the distances? They are. And since they're a scalar, do I care about the angles? Then you know what? As a shortcut, instead of finding each of these and adding them together, what would be a quicker way to do this since the charges and the distances are the same? Find the voltage for one and then do what? Times by 2. We're going to do that. So we're going to say this times 2. Is that okay? By the way, I like this question. In fact, they like this question. The provincial used to love this because the diamond shape was so terrifying to kids. But it's a scalar. So it's going to be 9 times 10 to the 9th. Positive 2.5 microcoulombs, 0.2, and then since they're identical, I'm going to double it. How many volts are at location X? $200,000? 225,000? Anybody else? Yeah? So right there is 225,000 volts. Every coulomb of charge would have 225,000 joules of energy. Direction, scalar. What does part B want me to find? Mick, what does part B want me to find? Oh, not X, Mr. Newick. It's going to be KQ over R Y. Now, again, Mick, normally if these were two different charges, I would find the voltage from there, I would find the voltage from there, and I would just add them up, and I would add them up scalars, I don't care. But what do you notice about both the charges? They are the same. What do you notice about both the R's, the distances? They are the... So you know what? As a shortcut, I'm just going to say I can go... It's going to be 9 times 10 to the 9th, positive 2.5 times 10 to the negative 6, all over 0.35, times 2. You okay with why we're timesing by 2? There's a lovely shortcut because this is a nice symmetrical picture. How many volts are there at location Y? 128,000. 571. Point what? Okay. Volts. Really, I'd say 129,000 if this was the final answer. So there's a higher voltage at location X, a lower voltage at location Y. Okay. What does C want me to find? Between where? Between Y and X or between X and Y? X and Y? So it wants me to go X take away Y? Okay. There's my symbol for potential difference, change in voltage. Is going to be Vx take away Vy. 225,000 minus 128,571. You all hopefully still have that stored on your calculator, so you can use your answer button. What do you get? 96,430. Can I do that? That's to 4 sig figs. A little more than we need, but that's okay. So, moving from here to here, if X is my final location and Y is my initial location, there is a change in voltage, a potential difference of 96,430 volts. You can sort of imagine, Mac, that you would be traveling through 96,430 volts. All right. What's D want me to find? The work required, and I'm going to change this question a little bit. I'm going to have it go, no, that works, from Y to X, because I want final and initial. Yeah, from Y to X. Sorry, I was reading it backwards. From Y to X. Okay, work. Now, I could go change in potential plus change, but wait a minute. It's really going to be Q, change in voltage. How big is the charge that we're moving, according to part D? Millicoulombs, 1.25. times 10 to the negative 3. And how many volts is it traveling through? What's its change in voltage? 96430. How much work would it take? Sorry? 120.5? 121? 121 what? Joules. Okay. Put your pencils down for a second. Let's talk about what we're really saying here. Okay? I'd like you to just watch. I'm going to give you some examples. Okay, look up. This is important. So, what if instead we were moving from this location, which was 0.2 and 0.2, if we were going from there to there? Well, the voltage here would be 225,000. The voltage here would be 225,000. What would your change in voltage be? Nothing. So how much work would it take? Nothing. Now wait a minute, Mr. Duick. Why would it take no work? Because if you're moving a positive charge, aren't these guys repelling it? They would be repelling it until you got to there, and then they would be pushing it up faster. You would have to do work to move it for the first bit because you'd be pushing, and then you could let it go and it would fly on its own. Whatever work you put in, you would get back. If you moved from a symmetrical location, Shaq, he needs some help. He's dying. Oh yeah, give him an elbow. Thank you. He needs it, okay? So in our specific example then, what we're saying is, look, to move from here to there, these two positives are repelling the charge that we're moving. We're pushing, we're giving up energy, As soon as we get to here, though, we're going to get some of the energy back because now we can kind of stop working. We can let this positive charge go. It's going to move on its own. That's what we're saying in all this voltage potential difference diagram. So, pick your pencils up. If the charges begin and end at rest, then work will just be the change in potential energy, which is the charge times the change in voltage. It says, prove that if the charge Q begins and ends at rest, then the work done in moving Q is given. You know what? I already did right there. There was my proof. But it's worth writing down then. Work also equals Q times the potential difference. That is going to give us a very nice way to start to talk about things like lightning and parallel plates. And we're going to take a very different slant starting next class for the remainder of the unit. Instead of looking at point charges, we're going to try and look at a much nicer situation. So here's our summary so far. Voltage can be found using the definition if we know voltage equals energy per Coulomb. And if I tell you how much energy there is at a location, and I tell you how big the test charge is, then you know how many volts there are there. Also, this can be written, as Rachel pointed out. Can also be calculated from the point charge equation if we know what charge is creating the voltage. That's why I use a big Q here for the big planetary charge. And you notice I used a lowercase q in the previous one because that's the satellite charge at that location. Potential energy of a charged system can be found using K, Q1, Q2 over R. That was last day's lesson. Can also be found using the definition of voltage if you happen to know the potential difference Note, potential energy and potential are not vectors. So if we have several charges, just add them up. However, since they are scalars, include the positive or negative signs of the charges. Okay. Let this percolate for a bit, but number 1, number 2, three is good. Four is good. 5 is good. So far I've assigned everything, I know. 7 is good. Now, Mickey, my angel, not because you're giggling, but because this relates to the question you asked. Number 7, what are they asking me to find? Did they say velocity or speed? Oh, this suggests a scalar approach. It's a proton accelerated, so I think there's a change in height, change in speed. You know what? I would use for number 7, except for that, did they tell you 2 charges? Read the question. Can you go K, Q1, Q2 over R? No. What did they give you a before and after of? Voltage. I would use, oh, this is the equation that's going to end up, Mickey, this is the equation that I like this question, I like this question, I like this question. This is the equation, Josh, where you're going to end up with a V for voltage and a V for speed. But you can now, this is particle accelerators, which we're going to start to talk about next lesson a little bit. So number 7 I like. Skip 8. Number 9 I like. I like. I'll pause there. Okay. Quick like a bunny.